For the question 1, the question is use the substitution method to integrate the following definite integral. The equation is integral 3, 0, 8x bracket 2x cube plus 3 dx, and then we take the constant out and use the derivatives to dx, and we get 8 integral t 30 bracket 2x square root of 4 plus 3x, and then let 3x equal to u, x equal to 1 over 3u, du over dx equal to 3, dx equal 1 over 3 du. When x equal to 3 and u equal to 9, we just sub in the equation, and we get 8 integral 90 bracket 2 bracket 1 over 3u square root of 4 plus u bracket 1 over 3 du. And we just multiply the 1 over 3 to the equation, and we get 8 over 3 integral 90 2 bracket 1 over 81 u square root of 4 plus u du. And we multiply the 2 in this equation with this in the bracket, and we get 8 over 3 integral 90 bracket 2 over 81 u square root of 4 plus u du. And after that we use the derivative of du to sub in the equation, and we get 8 over 3 bracket 2 over 81 bracket u square root of 5 over 5 plus u square over 2 bracket 90. And then the last is we just minus the equation after we sub in the 9 and 0 from the equation, that is u equal to 9 and u equal to 0, that we get 8 over 3 bracket 2 over 81 bracket 9 square root of 5 equal 5 plus 9 square over 2 minus 8 over 3 bracket 2 over 81 bracket 0 square root of 5 over 5 plus 0 square over 2, and we get the answer is 885.6.
Assalamualaikum and very good morning to Doctor and my fellow friend. My name is MOHAMMAD NAJHAN bin YUSOF. My metric number is 2777328. First, we are given that Q equals to 700 minus 2P plus 0.02Y, P equals to 25, and Y equals to 5000. Now we insert the P and Y into the equation, so we get Q equals to 700 minus 2 multiplied by 25 plus 0.02 multiplied by 5000. So we get Q equals to 750. To find the price elasticity of demand, we need to equate dQ over dP multiplied by P over Q. So we get negative 2 multiplied by 25 over 750. So the price elasticity of demand is negative 0.067. Next, to find the income elasticity of demand, we need to equate dQ over dy multiplied by y over q. So we get 0.02 multiplied by 5000 over 750. So the income elasticity of demand that we get is 0.13.
Hi, my name is DAREN. My metric number is 2777060. I will be discussing about question 3. The following cos cubic function, first we must find the critical point, and second determine if at this point the function is at a relative maximum, relative minimum, inflection point, or saddle point. First we got the equation, which is 3x cubed plus 1.5y squared minus 18xy plus 17. So to start off, we must find the critical point first, and critical point occurs when fx equals to 0 and fy equals to 0. And we find that fx equals to x squared minus 2y equals to 0. And for the fy is y minus 6x equals to 0. And after that, we substitute y equals to 6x into x squared minus 2y equals to 0. And we find out that x equals to 12 and also 0. And then we substitute x equals to 12 and 0 into y minus 6x. And we find the y equals to 72 and y equals to 0. So the first critical point shows that the first critical point is x equals to 0 and y also equals to 0. And the second critical point is x equals to 12 and y equals to 72. Next, we must determine if at this point the function is at relative maximum, relative minimum, and inflection point or setup point. So we must do the second derivative test, which shows that fxx times fyy minus fxy squared, and we get the equation of 54x minus 324. So at the first critical point, we substitute 0 into the x, and we get the answer of negative 324, which less than 0. Thus, it has a setup point at the first critical point 0 and 0 by the second derivative test. And at the second critical point, which is x equals to 12 and y equals to 72, we find the answer. We get the answer of 324, which is the positive number and greater than 0. Thus, it has a relative minimum at the second critical point, since the fxx we find out that is greater than 0. That's all from me.
Today, Dr. I'm Saisufen. I'm going to present about the solution for question 4. Here we have a minimum cost function and subject to an inequality constraints. First, we transform them into a Lagrange function form, then get this answer. Then we find out the Lagrange equation for each variables by using the partial derivative. We have three variables here, x, y, and lambda. In Kahn-Tucker conditions, we must follow the non-negativity conditions. It means that x, y, and lambda are bigger or equal to 0. And also, for the minimization, we must put Lagrange x and Lagrange y equations are bigger or equal to 0 after we do partial derivative. Then count out the first, second equation. For the Lagrange lambda equation is smaller or equal to 0 after we do partial derivative. Then it becomes the third equation. Since three variables and equations are equal to zeros, we can also rewrite the equations like this way. Now we assume that lambda is equal to 0. We substitute the 0 into the first and second equations. Then we get that x is 8 and y is 16. Then we substitute x is equal to 8 and y is equal to 16 into the constraint equations. So we get 24, which is bigger than 20. So it is fulfilled and by our constraint equations, which is x plus y is bigger or equal to 20. Then we substitute x is equal to 8 and y is equal to 16 into the cost function. And finally, we get the minimum values is negative 517.6. That's all for me. Thank you.
Good morning to sir and my fellow friends. My name is Yan and my matrix number is 277137. I'm going to present on the mathematical economics. Today I'm going to focus on question 5. So by explaining the step to answer the question 5. So let's move on to the questions. The question given is optimize the following function using A Cramer rules for the first order condition and also the Hessian for the second order conditions. And the equations are given. So as the part A request, we are going to use the Cramer's rule to solve the first order conditions. So first of all, we have to derivative it, a partial derivative. So for the x1, x2, x3, so we can get the both three equations, and also the three equation we are going to let it equal to 0. After we get these three equation, we are going to rearrange it. So for the first column will be x1, second column will be x2, and the third column will be x3. And also for the numbers without x, we are going to put it at the right hand side. So we get these three equations. So the next step we are going to do is we generate it, or we change it into a matrix form. And also the next step is we are let A equal to this 3.3 matrix. So we have to find the determinant of A. So after we determine it, we get the answer is 448. And also after we get it, we will have to find the x1, x2 and x3 value. So how to get it? Actually, we have to use the determinant of A1 divided by the determinant A that we found is 448. So we can get the x1 is 0.08929 and also x2 is equal to 0.4107 and also for the x3 is equal to negative 0.0179. So the three answer we get. So for the B part, we are going to do the Hessians for the second order condition. So we are going to do partial derivative again for the x1 equation and also x2, x3 for the y x1 equation. And continuously we are doing for x1, x2, x3 for the y x2 equation and also for x1, x2, x3 for the y x3 equation. So we get the nine numbers. So from this 9 number, we are going to put it at the Hessian form as in the matrix, which according to the y x1 x1, y x1 x2, y x1 for the orders that we have to follow. So after we putting it, insert the every number on this, we are going to find the D1 determinant. For D1, we can get the 6. Which is more than 0, and also D2 determinant for D2 is 71. We also know that is more than 0, and also for the last one is determinant for D3 is 448. It also obviously is more than 0. So from here we can conclude that it is positive definite. So it is minimum at the x1, x2, x3 that the three figure that we found and the part A. So that's all from me. Thank you.